For 200 years, humanity held the cure for one of its deadliest diseases and kept dropping it. Sailors died of something a fruit could fix, while the answer waited in the next barrel, the next forgotten notebook, the next voyage home. This is what it costs to forget a cure you already had. Take the orange on your kitchen counter, the juice you poured this morning without a thought. That molecule was once the only thing standing between a sailor and a death that began in the scars and ended in the bones. The cure was cheap, the cure was obvious, and for 200 years, it refused to stay found. This is the story of a disease that killed more sailors than storms, battles, and shipwrecks combined, and of the people who kept rediscovering the answer, watching it work, and letting it slip away, until, at last, someone asked why. On a gray afternoon in September 1740, several hundred old men limped up the gangplank of HMS Centurion. Most were Chelsea pensioners, veterans who had traded their pensions for one last chance at prize money. Some were 60, a few were pushing 70. Their commanding officer, George Anson, was taking them around the world. Within 10 months, more than 1,300 of the 1,854 men who had sailed were dead. Most never saw combat. Most never sighted the enemy. They died at sea, slowly, of something no one on board could name. By the time Anson's flagship limped back into English waters 4 years later, only 188 men were left alive. The published account of the voyage was compiled by Richard Walter, the ship's chaplain, though historians have established that the text was in fact ghostwritten by Benjamin Robbins, who never sailed. What the pages record, in spare and terrible prose, is not the language of medicine, but the language of a man watching the body come apart. There is the sailor who watched a wound he had carried for 50 years reopen on his own arm. The skin that had knit closed over a half-century-old injury simply stopped holding. There is the man whose old fracture, healed so long ago that he had forgotten it, began to ache as though it had just been made. The very stuff that holds a body together was failing. No one knew that yet. They only knew that the seams were coming loose. The ship itself became the architecture of the dying. Below decks, in the airless holds, the men lay in rows on the planking. The lower decks were sealed against the weather, and the air inside grew thick and damp. Above them, the officers walked the quarterdeck in clean coats, reading logs and watching the horizon. Below, the bodies failed one by one, the men too weak to climb the ladders, the living and the dead packed close in the half-light. What they ate made it worse. Salt pork, hard biscuit, the occasional weevil. Everything that kept on a long voyage was dry, salted, or pickled, because anything fresh would rot. Scurvy grass, the traditional remedy, grew on a few cold shorelines and did almost nothing. Aboard the Centurion, the diet was the same diet every sailor ate, and the disease was the same disease every sailor feared. By the time the fleet had rounded Cape Horn and fought its way into the Pacific, the men below decks were coming apart at a rate the surgeons could do nothing to slow. And what made it strange, what made it almost unbearable to read about now, was that the body was not rotting. The flesh was not falling away. The men simply lost the ability to repair themselves. Old injuries returned. New ones would not heal. The inside of the body was quietly losing the capacity to hold itself together. This was not unusual. Long voyages routinely lost half their crews. Some lost more. Between the 16th and 18th centuries, more than 2 million sailors died of it. More than storms, shipwrecks, combat, and every other disease at sea combined. No single force on the water killed more men than this quiet failure of the body to remain itself. And the strangest part, for 200 years, the cure kept being found. And every single time, it kept being lost. The first time the cure appeared in the record, it was already slipping. In the spring of 1498, Vasco da Gama's fleet had rounded the Cape of Good Hope, and was sailing up the East African coast. His crew was dying by the dozen. Out of 170 men, 116 would never see Portugal again. Among the dead, almost all of them died of the same quiet failure Anson's men would die of, 2.5 centuries later. When the fleet made landfall near what is now Mombasa, da Gama sent a boat ashore for oranges. His men were desperate for them. The locals traded them. The men who could still eat them recovered. The voyage continued, and the cure that had just saved a dozen lives vanished into the logbook, unread. 40 years later, Jacques Cartier was frozen into the St. Lawrence River. It was the winter of 1535, and by February, 110 Frenchmen had been reduced to 10, who could still help the others. Their bodies were failing. Their old injuries were reopening. They lay in their cold cabins and waited to die. Then, an Iroquois man named Domagaya, one of 2 sons of Chief Donnacona, whom Cartier had taken back to France as captives on his first voyage, told Cartier about aneta, a decoction brewed from the bark of a single tree. The men drank it. Within a week, approximately 85 of them were back on their feet. The cure worked spectacularly. Cartier sailed home in the spring, and he never learned which tree had cured his men. The knowledge passed out of the hands of the only men who had ever seen it work, and back into the silence of the Canadian winter. By the 1500s, the practice of dashing ashore for fresh fruit had become routine. Dutch and Flemish captains on Iberian routes knew that oranges could revive a dying crew. They treated it the way a sailor treats any other supply problem: a quick stop, a few baskets bought, on with the voyage. It worked every time, but it never became knowledge. It stayed an informal habit attached to a single voyage, dying with the voyage. A century passed, then another. In 1593, the naval commander, Sir Richard Hawkins, watched his crew suffer the same disease off the coast of Brazil and noted, almost in passing, that oranges and lemons ended it. He wrote this down. It changed nothing. In 1617, John Woodall, Surgeon General of the East India Company, published a book called The Surgeon's Mate, and inside it, he gave the most explicit instruction anyone had yet given: send lemon juice aboard every ship. The advice was correct. It was also buried inside a long recipe that mixed the juice with herbs, wine, and a dozen other ingredients, so that no one who read it could tell which part was doing the work. The pattern is the same in every case. Someone on the ship, with no theoretical framework and no idea why it worked, watched a fruit cure the dying. They wrote it down, or they didn't. They sailed home. And when the next voyage went out, the next crew took the same salt pork and the same dry biscuit, and the same disease came back, because no one had built a structure around the cure that would let it survive the return trip. That is the question this episode keeps asking. Each time the cure is found, the next question is whether this one will stick. For 200 years, the answer was no. And then came May of 1747, and a 30-year-old Scottish surgeon named James Lind, who would, for one brief moment, change the shape of the question. Lind was aboard HMS Salisbury in the Bay of Biscay. Scurvy had broken out in the crew. Lind picked 12 men who were as sick as each other, laid them in the forehold, and divided them into 6 pairs. To each pair he gave a different treatment. Cider to one, sulfuric acid mixed with water to another, vinegar to a third, seawater to a fourth, a paste of garlic, mustard, and horseradish to a fifth, and to the 6th, 2 oranges and 1 lemon. 6 days later, only the citrus pair was fit to nurse the others. The rest were still sick, or worse. It was, in its small way, one of the cleanest comparative trials anyone had ever run. Lind had taken a remedy that existed as scattered anecdote in the logbooks of a dozen voyages, and he had tested it the way you test anything. He had put it up against the alternatives, on matched patients, under the same conditions. The oranges had won. This is the moment everyone remembers. It is the moment history textbooks pause on, the moment 1,000 medical history lectures pause on, the moment that makes James Lind a household name in schools. And it is, in fact, only the second most important thing that happened on that ship. The most important thing is what Lind did next. He sat on the result. For 6 years, he did not write a pamphlet. He did not send a letter to the Admiralty. He did not call a meeting of surgeons. He kept the finding in his notebook, and he let another 100,000 men go to sea and die of the same disease. When he finally did write in 1753, he produced a book of roughly 400 pages, a treatise of the scurvy. It is the book that ought to have ended scurvy, and it is also, in many ways, the reason scurvy kept going. Because buried inside those pages, alongside the Orange Trial and the unequivocal results, Lind laid out his own theory of what caused scurvy, and his theory was wrong. Lind believed scurvy arose from a kind of internal putrefaction of the body, aggravated by damp sea air and a constipating diet, and that citrus worked because its acid corrected that putrefaction. It was a tidy explanation. It was also completely false. And because Lind was now associated with the wrong theory, his right result started to look like a footnote to it. By the time he had revised the book 3 times, the lemon finding was so swamped by caveats and alternatives that a careful reader could come away thinking Lind himself was uncertain. The Sick and Hurt Board, the body that ran medical care for the Royal Navy, considered Lind's proposal in 1754 and turned it down. Not because the oranges had failed, they had not. They turned it down because Lind had not solved the second problem that no one else on the planet had solved either: how to keep lemon juice from rotting on a long voyage. The juice went bad. Lind's own recommended preservation, a boiled down syrup he called Rob, destroyed much of the active ingredient. And without a stable, shippable concentrate, an Admiralty order was useless. The competing theories took the room that Lind had given up. Sir John Pringle, president of the Royal Society, argued that scurvy came from a lack of fixed air in the tissues. David McBride, an Irish surgeon, treated patients with fermented malt and wrote that it worked. Neither of them was right, but both of them sounded like medicine. Both of them had a mechanism, even a wrong one. Lind's correct empirical result was now floating free, unattached to a theory, vulnerable to anyone with a more scientific-sounding story. It took 40 years. 40 years between the trial and a mandate. The breakthrough finally came from Gilbert Blaine, another naval surgeon, who cracked the storage problem Lind never cracked. Blaine showed that adding a small percentage of alcohol to the juice kept it potent for the months a long voyage required. In 1793, a fleet Blaine had equipped reached Madras after 19 weeks at sea without a single case of scurvy on board. 2 years later, in 1795, the Admiralty issued a standing order. Every sailor in the Royal Navy would receive a daily ration of lemon juice, mixed into his grog. By then, James Lind had been dead for a year. He died in 1794, having seen his empirical result confirmed by half a century of other people's voyages, and having watched his own navy do nothing about it. The cure that had taken him 6 days to find had taken the Royal Navy 40 years to adopt. And then it stuck. For about 60 years, it actually stuck. Scurvy cases in the Royal Navy collapsed. At Haslar Naval Hospital, roughly 1 in 5 admissions during Lind's tenure showed signs of scurvy, with hundreds of deaths recorded in years like 1780. By 1810, the number was effectively 0. The British Empire, with a fleet that could now stay at sea for months without dissolving, became the most powerful naval force on Earth. Nelson won Trafalgar with a navy that no longer rotted from the inside. The cure had found its place. It would lose it again. Around 1860, a quiet substitution took place. Mediterranean lemons, the fruit whose juice had ended scurvy, were replaced in the Admiralty supply contracts by West Indian limes. The change was administrative. The two fruits were called by each other's names in common speech, and British colonial plantations in the Caribbean could produce lime juice far more cheaply than Mediterranean lemons could be shipped in. The juice was also more acidic on the chemist's tests of the day, which was taken as a sign it was stronger. It was not stronger, it was much weaker. Later, measurements put the anti-scorbutic power of fresh lime juice at roughly a quarter to a half that of fresh lemon juice. The copper-lined vats the Navy stored it in, and the copper piping it traveled along, destroyed much of what was left. By the time a sailor drank his daily ration in the late 19th century, the dose he was getting was a fraction of what Blaine's original order had intended. The cure was now legal, routine, and almost entirely useless. It did not work, and it failed in places where the failure was undeniable. In 1875, the British Arctic expedition under George Nares sailed north with a full lime juice ration aboard. Within days of leaving the ship, men on the sledging parties began to fail. Within 5 weeks, half of them were sick. And, tellingly, some of the men who stayed aboard ship and faithfully drank their daily lime juice also developed scurvy. They were doing exactly what they had been ordered to do. They were following the cure. The cure had been replaced. The Admiralty convened a parliamentary committee of inquiry in 1877 to investigate a disease that had been, officially, solved 80 years earlier. The committee's report described cases where men who had dutifully taken their daily dose still came down with scurvy. The committee was unable to explain why. Polar expeditions in the early 20th century still lost men to it. Robert Falcon Scott's 1910 expedition, sledging south with a carefully calculated ration of pemmican and biscuit and butter, was functionally devoid of vitamin C. The expedition's physician treated cases of scurvy in the second winter. Edward Evans, the expedition's second-in-command, was invalided home on the relief ship with scurvy so severe he nearly died. The polar party that died returning from the South Pole in 1912 may have been weakened by other causes, but scurvy was in the hut with them, and everyone knew it. The merchant marine never got the order at all. Captains on the China tea routes, on the Australian wool routes, on the West Indies sugar routes, ran on lime juice that did almost nothing, and lost men the Royal Navy had stopped losing decades earlier. It was not only at sea. Scurvy continued to kill in prisons, in workhouses, in Irish famine populations. Most quietly of all, it killed in the nurseries of wealthy European and American families, where babies were fed pasteurized cow's milk. The heat destroyed the vitamin C, and infantile scurvy reappeared in the late 19th century as something that looked, to doctors who had never seen it, like an entirely new disease. This is what makes the second half of the cycle so strange. The British Navy had not forgotten about citrus. It had issued it every day for nearly 70 years. It had not abandoned the theory. There was no theory. It had simply changed the fruit and then watched the disease reappear without understanding why. The cure kept slipping across all those years and all those voyages, not because the men who held it were stupid. They were not stupid. They were often the most accomplished surgeons of their generation. Lind, Pringle, McBride, Blaine, Woodall, Hawkins. They were at the top of their profession. They kept losing the cure because the cure was an empirical fact, floating free of any theoretical scaffold. They knew that citrus worked. They could not tell you why. A fact without a mechanism is a fragile thing. It can be replaced by any other fact that comes with a theory attached. In the 18th and 19th centuries, there was no shortage of theories about scurvy, and almost all of them had champions who sounded more scientific than a man saying, "Just give them oranges." Lind himself, as we have seen, blamed a kind of internal putrefaction aggravated by damp air and a constipating diet. The sea air was damp. The body could not evacuate its corrupt humors. Citrus worked because the acid corrected the rot. It was a tidy explanation, internally elegant and completely wrong. Pringle and McBride blamed a deficiency of fixed air in the tissues, and they prescribed fermented malt. The great Dutch physician Boerhaave thought it was the salt meat rotting inside the sailors' bodies and producing an internal putrefaction. In the germ theory era, scurvy was briefly reclassified as a kind of ptomaine poisoning from tainted tinned meat. Other doctors blamed cold, damp, fatigue, depression, homesickness, bad morals, copper cookware, the magnetic influence of iron hulls. The cataloger Francis Rachel Frankenberg counted dozens of confident, mutually incompatible explanations, each with its own champion, each with its own prescribed remedy. Each of these explanations was wrong, and each was more plausible sounding on a medical school examination paper than the simple admission that a particular fruit prevented a particular disease for reasons no one understood. What Lind did to his own finding is the perfect example of the trap. He buried the citrus result inside his own wrong theory. He gave every rival a target. He made the lemon look like one more remedy in a polypharmacy of options, instead of the answer. By the third edition of his treatise, the lemon finding was so diluted by caveats that a careful reader could come away thinking Lind himself was not sure. The empirical fact was sitting on the table. It just had no armor on. This is the deep reason the cure would not stick. It is not that the men of the 18th century were careless, or that the Admiralty was slow, or that the merchant marine was forgotten. All of those things are true, but they are symptoms of a single underlying condition. A cure without a mechanism is a temporary fact. It survives one generation, sometimes two. Then it gets nudged out, or substituted, or simply forgotten, and the disease comes back. To see what it looks like when the mechanism arrives and the cure becomes permanent, you only have to follow the story a few decades further. In 1907, two Norwegian researchers, Axel Holst and Theodor Froelich, did something that sounds almost mundane. They fed a group of guinea pigs a restricted diet. They watched the guinea pigs develop scurvy. For the first time in history, an animal model of the disease existed. Until then, every claim about scurvy had rested on human observation. Now, a controlled experiment was possible, and the entire field could begin to behave like a laboratory science instead of a collection of voyage logs. 5 years later, in 1912, the Polish biochemist Casimir Funk gave the broader class a name. He called them vitamins. Accessory dietary factors present in tiny amounts, whose absence produced specific deficiency diseases. The word did not yet describe a single molecule. It described a category. In 1928, a young Hungarian researcher named Albert Szent-Györgyi, working in Cambridge and then in Szeged, began isolating a substance from adrenal glands and, later, from paprika. He called it hexuronic acid. By 1932, working with an American colleague named Joseph Sverbelie, he had proved that hexuronic acid was the anti-scorbutic factor. The molecule that cured scurvy had a name. It had a structure. It had, for the first time in 200 years, a mechanism. That mechanism was the one Lind had never had. Vitamin C, ascorbic acid, is the cofactor the body uses to build collagen. Without it, the protein that holds skin, blood vessels, cartilage, and bone together cannot form correctly. Old injuries reopen because the healed tissue cannot be maintained. New injuries cannot close. The seams come loose in the most literal possible sense. Now, finally, the cure had an explanation that tied the empirical observation to the underlying chemistry of the body. And that is what made it permanent. Not the orange, not the lemon, not even the molecule, the explanation. Once ascorbic acid was named, isolated, and understood, no Admiralty clerk could quietly substitute a less potent fruit. Once the dose-response relationship was quantified, no expedition planner could leave vitamin C out of a sledging ration by accident. Once the mechanism was understood, every prior rediscovery stopped being a lucky accident and became a verification of a known law. The cure was the same cure it had always been. It had just, at last, been given a why, and from that point forward, it would not slip again. A hand reaches across a kitchen counter and picks up an orange. The peel splits under the thumb. The juice falls into a glass without a thought. That is the entire cost. Bodies coming apart at sea. Cures found and forgotten. A mandate issued decades too late. A fruit quietly replaced by a weaker one. All of it ending in this glass. The cure had always been a fruit. What changed was that humanity finally learned why. What is a cure that everyone swears by, but no one can quite explain? Tell us in the comments. Subscribe to the Origin Portal, and we will see you at the next beginning.